The morning of February 19th, 1945. 7 miles off the volcanic shores of Iwo Jima. The grey dawn broke over an armada unlike anything the Pacific had ever witnessed. Nearly 800 naval vessels stretched across the horizon, their silhouettes emerging from the pre-dawn darkness like a steel city rising from the sea. Among them, over 100 landing ship tanks, ungainly flat-bottomed behemoths that sailors called large slow targets, wallowed in the swells, their cavernous holds packed with Sherman tanks, artillery pieces, ammunition, fuel, and the machinery of invasion. Inside LST 779, 23-year-old Coxswain James Fahey from Waltham, Massachusetts, stood at his battle station, feeling the ship roll 40 degrees in seas that barely troubled the destroyers racing past. Through the open bow doors, he could see the volcanic sand of Iwo Jima's beaches, black as coal, waiting. In the tank deck below, 14 Sherman tanks sat, secured, their crews already mounted, engines idling, filling the enclosed space with diesel fumes, despite the ventilators running at full capacity. On the weather deck above, trucks, jeeps, and supplies sat lashed down, along with 36 Higgins boats that would ferry additional troops to shore. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The ship's captain, Lieutenant Robert Landis, checked his watch. H-hour, minus 30 minutes. In half an hour, the bow doors would swing open, the ramp would drop onto volcanic sand, and 20 years of American tanks would thunder directly onto an enemy-held beach without need of docks, cranes, or ports. This capability, which would prove decisive in winning the war, had not existed 3 years earlier. The ship beneath Fahey's feet, this unglamly vessel that creaked and groaned in moderate seas, represented one of the most revolutionary achievements in naval architecture and industrial production in American history. The story of how these ships came to exist, how American industry learned to build ocean-going vessels in inland rivers, and how one company's desperate innovation reduced construction time from 4 months to 72 hours, begins not in the Pacific, but in the steel mills and rivers of Pittsburgh, Pennsylvania, where an engineering challenge considered impossible by the Navy's Bureau of Ships was solved by men and women who had never built a sea-going vessel in their lives. The crisis began in the summer of 1940, in the smoke-filled rooms of the British Admiralty in London. Winston Churchill paced before a wall map of Europe, studying the coastline of occupied France. The Prime Minister had championed amphibious warfare since his disastrous Gallipoli campaign in World War I. He understood with brutal clarity that Britain would need to return to Europe someday, and when that the day came, they would need to land armies directly onto defended beaches. The Germans controlled every port from Norway to Spain. Conventional wisdom said amphibious invasion required the capture of ports with their docks, cranes, and unloading facilities. But ports were fortress strongpoints that could be held by relatively small forces. Any invasion concentrated on capturing a port would face devastating defensive fire. Churchill needed something different. He needed a ship that could cross the Atlantic Ocean, survive North Sea storms, approach an enemy beach, and discharge tanks directly onto sand. Not landing craft that required transport ships to carry them close to shore. A proper seagoing vessel that could make ocean voyages independently and land its cargo without any shore facilities whatsoever. The British had already developed the Landing Craft Tank, or LCT, a shallow draft vessel with bow doors and a ramp. But LCTs were too small for ocean crossings. They could carry only 5 tanks, had to be transported in sections, and were unsuitable for the North Atlantic. What Churchill envisioned was something far larger and more capable. He called it an Atlantic tank carrier, a ship that combined the seaworthiness of an ocean-going freighter with the beaching capability of a landing craft. The British took their requirements to the United States Navy's Bureau of Ships in November 1941. The timing was deliberate. Britain desperately needed American production capacity. The US Navy, though not yet at war, was already gearing up for what seemed inevitable. Representatives from both navies met in Washington to discuss specifications. The requirements seemed contradictory to the point of impossibility. The vessel needed to carry at least 20-30-ton Sherman tanks, traverse the Atlantic Ocean independently, have enough range to cross the Pacific if necessary, beach itself on hostile shores, discharge its entire cargo in under an hour, then pull itself off the beach, and return for another load. It needed a large ballast system to provide deep draft for ocean travel, but shallow draft for beaching. It required bow doors strong enough to withstand ocean swells, but light enough to open quickly under fire. The design had to be simple enough for rapid mass production by shipyards that had never built such vessels. John Niedermeyer, a 51-year-old naval architect serving as technical director of preliminary ship design for the Bureau of Ships, took the requirements back to his office. He had spent 3 decades designing everything from battleships to submarine tenders. But this project presented challenges unlike anything he had encountered. A ship that could operate in both deep and shallow water violated fundamental principles of naval architecture. Traditional ships had fixed drafts determined by their hull shape and cargo weight. You couldn't simply vary a ship's draft by 18 feet depending on whether you wanted to cross an ocean or approach a beach, unless you could. Niedermeyer worked through the problem systematically. The solution would require a massive ballast system, far larger than anything used on conventional ships. During ocean transit, seawater would flood into ballast tanks throughout the ship, giving it sufficient draft to handle rough seas. When approaching the beach, pumps would empty these tanks, raising the ship higher in the water and dramatically reducing the forward draft. He sketched a vessel with an unusually wide beam relative to its length. Where a destroyer had a length-to-beam ratio of 10:1, his design would be 6:1. This broad, flat-bottomed configuration would distribute the ship's weight over a larger area, allowing it to rest on the beach without capsizing. For the bow, Niedermeyer envisioned massive clamshell doors that would swing open, revealing a hinged ramp that could drop directly onto the beach. The ramp needed to support 30 tons, the weight of a fully loaded Sherman tank. The doors had to seal watertight for ocean crossings, but open quickly during landing operations. Behind the bow doors would be the tank deck, a vast open space running nearly the entire length of the ship, high enough to accommodate the tallest military vehicles. Within days, Niedermeyer had produced a preliminary sketch. The design was sent to the British Admiralty on November 5, 1941. The response came back almost immediately. Approved. Britain wanted 200 of these vessels built as quickly as possible under the Lend-Lease program. The ship would be designated the Landing Ship, Tank Mark II, or LST. History would simply call it the LST. But approval of the design was only the beginning. The real challenge would be construction. In January 1942, just weeks after Pearl Harbor plunged America into the war, the Navy faced a critical bottleneck. Coastal shipyards were already overwhelmed, building destroyers, cruisers, aircraft carriers, submarines, liberty ships, and escort vessels. Every berth in every major shipyard was spoken for years in advance. Where would America build over 1,000 LSTs? Admiral Samuel Robinson, chief of the Navy Bureau of Ships, studied the problem. LSTs required relatively shallow water for launching, nothing like the deep water berths needed for battleships or carriers. Their flat bottoms and shallow draft meant they could be built in rivers and waterways normally unsuited for ship construction. The American Midwest, with its extensive river system connecting to the Gulf of Mexico, had steel mills, heavy industry, and waterways deep enough for LST construction. But the Midwest had no tradition of shipbuilding. The nearest ocean was 1,000 miles away. In January 1942, less than 2 months after Pearl Harbor, Admiral Robinson approached Frank Dravo, chairman of Dravo Corporation, a Pittsburgh-based company that had been building barges, tugboats, and river vessels since 1891. The meeting was brief and direct. The Navy had designs for a revolutionary invasion craft. They needed it built immediately in quantities that seemed impossible. Could Dravo do it? Frank Dravo and company president Victor Edwards studied the preliminary designs. The specifications called for a vessel 328 feet long, 50 feet wide, displacing over 4,000 tons when fully loaded. It would be the largest vessel ever constructed in Pittsburgh. It would require techniques, materials, and skills that Dravo workers had never used. The Navy wanted the first ship in 6 months. Then they wanted dozens more, then hundreds. Most companies would have said it couldn't be done. Dravo said yes. The decision transformed not just Dravo Corporation, but the entire industrial landscape of Pittsburgh and the Ohio River Valley. Within days of accepting the contract, ground was broken for a massive expansion of Dravo's existing facility on Neville Island in the Ohio River just west of Pittsburgh. The original plant became the West Yard. A 66-acre riverside field was transformed into the East Yard. What had been swampland and empty fields in February became construction sites in March and operational shipyards by summer. But the physical expansion was only part of the revolution. The real innovation came in how Dravo approached the construction process itself. Traditional shipbuilding, the method used for centuries, involved building vessels piece by piece on the shipways. Skilled workers would assemble the keel, then the ribs, then the hull plates, working from the bottom up. Each ship was essentially hand-built, with craftsmen performing every operation on site. A vessel of LST size, built by traditional methods, would take 8 to 12 months to complete. Dravo didn't have 8 months. The Navy needed these ships yesterday. Victor Edwards and his chief engineer, James Fahey, studied Henry Ford's automobile assembly lines and the techniques being pioneered at the Kaiser shipyards on the West Coast for Liberty ship production. What if they could break LST construction into modular sections? What if, instead of building the ship piece by piece on the shipways, they prefabricated large sections at separate facilities, then brought them together for final assembly? The plan was audacious. Dravo would create 5 separate fabrication plants throughout the Pittsburgh area. Each plant would specialize in building specific sections of the LST. One facility would construct the bow sections with their massive doors and ramp assemblies. Another would build the stern sections housing the engines and crew quarters. A third would fabricate the flat bottom sections. 4th and 5th plants would produce the tank deck bulkheads and the weather deck structures. These enormous prefabricated sections, some weighing over 50 tons, would be transported by rail and truck to Neville Island for final assembly. This modular approach solved multiple problems simultaneously. First, it dramatically increased production speed. Instead of one team building an entire ship sequentially, dozens of teams could work on different sections of multiple ships at the same time. Second, it made training workers much easier. Instead of requiring skilled shipwrights who understood every aspect of vessel construction, Dravo could train workers on specific tasks. Someone who had never seen a ship before could learn to weld bulkhead sections in a few weeks. Third, it allowed Dravo to leverage Pittsburgh's existing industrial infrastructure. The city's steel mills, fabrication shops, and heavy equipment manufacturers could all contribute components without retooling their entire operations. But modular construction created its own challenge. How do you connect these massive prefabricated sections into a seaworthy vessel? The traditional answer was riveting. Steel plates were overlapped and punched with holes. Then hot rivets were driven through the holes and hammered to create a mechanical connection. Riveting was slow, labor-intensive, and required overlapping material that added weight. More critically, riveted joints had inherent weaknesses. Stress could cause rivets to fail. In cold water, riveted ships could develop leaks as the metal contracted. James Fahey proposed an alternative that the Navy Bureau of Ships initially resisted: electric arc welding. Welding technology had advanced significantly during the 1930s. By 1942, electric arc welding could create continuous joints between steel plates that were actually stronger than the base metal. Welded joints saved steel because plates didn't need to overlap. They were lighter, faster to produce, and when done properly, absolutely watertight. But welding had a dark reputation in shipbuilding. In 1939, several welded cargo ships had suffered catastrophic failures, literally cracking, in two during routine voyages. The Navy blamed welding technology and remained deeply suspicious of welded ship construction. Dravo's engineers understood that the catastrophic failures weren't the fault of welding itself, but resulted from poor quality steel, inadequate training, and design flaws that allowed cracks to propagate across welded joints. With proper steel alloys, trained welders, and careful inspection, welded construction would actually be superior to riveting. The advantages were simply too significant to ignore. A skilled welder could join steel plates twice as fast as a riveting team. Welding could be done anywhere, not just in the cramped confines of a partially built ship. More importantly, modular prefabrication absolutely required welding. The massive prefabricated sections would need to be joined on the shipways in days, not weeks. Riveting couldn't possibly keep pace. If Dravo was going to build LSTs in months instead of years, welding was not just an option, it was essential. In April 1942, Dravo began recruiting welders from across the steel industry. The company also established welding schools to train new workers. These schools were revolutionary in their inclusiveness. Women were recruited and trained alongside men. African American workers, who had been systematically excluded from skilled positions throughout most of American industry, were trained as welders and given jobs at equal pay. Elderly workers who had been told they were too old for war production found themselves operating welding equipment. People with physical disabilities discovered they could weld sitting down. That precision mattered more than raw physical strength. By midsummer 1942, over 3,000 workers had been trained in electric arc welding. The welding schools continued operation throughout the war, ultimately training over 10,000 welders. The workforce at Dravo exploded from 1,500 workers in 1941 to 16,000 by 1943. The company operated 24 hours a day, 7 days a week. Over the main gate at Neville Island, a sign read, "We can, we will, we must." On June 10, 1942, exactly 7 months after the Navy first approached Dravo, the keel for LST-1 was laid down at the East Yard. The date was symbolic. 6 months earlier, Pearl Harbor had been attacked. 3 months earlier, the contract had been signed. Now, America's first LST was beginning construction at an inland shipyard that hadn't existed as a concept 12 months earlier. The construction process revealed the genius of prefabrication and welding. At 5 fabrication plants throughout Pittsburgh, teams worked simultaneously on sections for a dozen different ships. At one plant, workers assembled the bow doors and ramp mechanism. The doors were massive clamshells of 1/4-inch steel plate, each weighing several tons. The ramp, designed to support 30-ton tanks while being light enough to raise and lower quickly, used a honeycomb structure of steel reinforcement. At another plant, crews welded together the flat bottom sections, huge panels of steel plate 30 feet wide and 60 feet long. A third facility constructed the vertical bulkheads that would divide the tank deck from crew spaces. These sections arrived at Neville Island on railway flat cars and heavy trucks. Massive gantry cranes, some of the largest in the Western Hemisphere, lifted the prefabricated sections and lowered them into position on the shipways. Welders immediately began joining the sections. The process looked more like assembling a giant model kit than traditional shipbuilding. Within days, the distinctive shape of an LST would emerge. The long, flat deck, the towering bow doors, the low superstructure aft. LST-1 was launched on September 7, 1942, just 89 days after its keel was laid. The event made front-page news across America. Thousands of spectators lined both banks of the Ohio River near Emsworth, Pennsylvania. They climbed trees and crowded onto building roofs to watch. At precisely 1 o'clock in the afternoon, with a bottle of champagne smashed across her bow, LST-1 slid down the greased launchways into the Ohio River. The ship created a wake so large that waves crashed over the riverbanks, sending spectators scurrying to higher ground. Children cheered. Women wept. Men who had built the ship stood watching, their faces showing a mixture of pride and disbelief. Radio commentator Lowell Thomas, witnessing the event, captured the moment in his broadcast that evening. I, along with some 10,000 other people, attended a ship launching today, and I don't think either the Japanese or the Nazis would have enjoyed the ceremony. It was an ocean-going ship, built for Uncle Sam's Navy, built out here at Pittsburgh, and launched here at Pittsburgh. The most interesting thing about this sea-going vessel launched here in the Ohio River was that it came off an assembly line. An assembly line, that was the revolution. Not just that LSTs could be built inland, but that ships could be mass-produced like automobiles. Each LST constructed at Dravo benefited from the lessons learned building the previous one. Inefficiencies were identified and eliminated. Fabrication sequences were optimized. Welding techniques were refined. Templates and jigs were built to ensure identical sections could be produced at multiple plants and would fit together perfectly during final assembly. By 1943, the construction time for an LST at Dravo had been reduced to 4 months. This was already remarkable, faster than most coastal shipyards could build comparable vessels. But Dravo's engineers kept pushing. Could it be done faster? Every day saved in construction meant another ship available for the war effort sooner. Every hour cut from the process meant American troops would have the landing craft they needed for the invasion of Europe. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The breakthrough came from an unexpected source. In late 1943, Margaret Wilson, a 28-year-old welder who had learned her trade at one of Dravo's welding schools just 14 months earlier, noticed a problem with the sequence of welding operations on the bow ramp assembly. Workers were welding the structural reinforcements in a specific order prescribed by the engineering drawings, but this sequence required welders to work overhead and in cramped positions. Wilson suggested reversing the order. If they welded certain joints first while the sub-assembly was still lying flat, those welds could be done downhand with the workpiece below the welder, which was much faster and produced higher quality welds. Her supervisors were skeptical. The engineering drawings specified the sequence for structural reasons. Changing it might compromise the integrity of the ramp, but Wilson persisted. She consulted with James Fahey, explained her reasoning, and suggested a test. 2 teams would build identical ramp assemblies. One would follow the standard sequence. The other would use Wilson's modified approach. The results were dramatic. Wilson's team completed the ramp assembly in half the time, and ultrasonic testing showed the welds were actually superior in quality. The downhand welding position allowed welders to maintain better control. The ramp suffered less distortion from heat, because the stress was distributed differently during fabrication. Within a week, Wilson's sequence was implemented across all 5 fabrication plants. The time to construct a complete bow section dropped by 30%. This was only one of dozens of similar improvements suggested by workers throughout Dravo's operation. The company encouraged this kind of innovation through a formal suggestion program and maintained an open-door policy where any worker could approach management with ideas. The most valuable suggestions earned cash bonuses and recognition. More importantly, they were actually implemented if they proved effective. This created a culture where workers felt ownership of the production process and constantly looked for ways to improve efficiency. By early 1944, Dravo had reduced LST construction time to under 3 months. Then came the crisis that would test everything they had learned. On April 2, 1944, James Forrestal, Secretary of the Navy, arrived at Neville Island unannounced. He was driven directly to the office of Frank Dravo and Victor Edwards. The meeting lasted less than 10 minutes, but the stakes could not have been higher. Forrestal explained that Operation Overlord, the invasion of Normandy, was scheduled for early June. Intelligence indicated the operation would require every available LST, plus dozens more that didn't yet exist. The Navy needed 15 additional LSTs delivered by May 31st, 60 days. Could Dravo do it? 60 days meant completing one LST every 4 days. The current production schedule had LSTs finishing every 9 days. Forrestal wanted production doubled overnight. Edwards asked how critical this was. Forrestal's response was blunt. Without these ships, the invasion might fail. With them, we win the war. Edwards and Dravo committed without hesitation. They called it the Hot Ship Program. Every resource Dravo possessed would be dedicated to producing 15 LSTs in 60 days. The yards would operate at maximum capacity, overlapping production schedules so multiple ships would be under construction simultaneously at different stages. Workers would be asked to extend their shifts. Crews would work 12-hour rotations with minimal time between shifts. Every fabrication plant would operate beyond normal capacity. Sections that normally moved by truck would move by emergency rail. Suppliers throughout the steel industry would prioritize Dravo's orders. The workforce responded magnificently. Welders who had been working 8-hour shifts volunteered for 12 hours. Crane operators stayed on the job through meal breaks, eating sandwiches in their cab between lifts. Inspectors worked around the clock, examining every weld as soon as it cooled. The fabrication plants hummed 24 hours daily with the buzz of arc welders and the clang of steel on steel. Over the gates, new banners appeared. 15 ships by May 31, and the guy who relaxes is helping the Axis. The workers understood exactly what was at stake. These were not abstract products being manufactured for distant customers. These were ships that would carry their sons, brothers, and husbands onto the beaches of Normandy. Every hour saved in construction meant better odds for American troops. Every weld that had to be redone because of poor craftsmanship would delay another ship, potentially costing lives. The psychological pressure was immense, but it drove quality to extraordinary levels. Dravo developed new techniques specifically for the hot ship program. Prefabricated sections that had previously been transported individually began moving in matched pairs. Instead of lifting bow sections into place one at a time, cranes would simultaneously lift both port and starboard sections, positioning them in a single operation. This cut crane time in half and allowed welders to begin joining both sections immediately. The welding itself became more efficient through carefully orchestrated teamwork. Previously, welders had worked individually or in small groups, completing joints sequentially. During the hot ship program, welding became a synchronized operation. Teams of 6 to 8 welders would simultaneously attack different sections of the same seam, their arc lights flickering in patterns across the hull. The heat from multiple welders working simultaneously actually helped reduce stress and warping. The technique was risky. Improper coordination could create weak points where welds met, but when properly executed, it was dramatically faster. Inspection procedures were also streamlined without compromising safety. Instead of waiting for entire sections to cool before inspection, portable X-ray equipment was brought directly to the work site. As each section of weld cooled sufficiently, inspectors examined it immediately. Any defects were marked for repair while the welding team was still on site, eliminating delays. This continuous inspection process meant problems were caught and fixed in real time, rather than discovered days later after workers had moved to other tasks. The intensity of the hot ship program generated its own problems. Workers pushed beyond normal fatigue limits made mistakes. The error rate crept up slightly during the first 2 weeks. Dravo responded by instituting mandatory rest periods. No worker could work more than 12 hours in a 24-hour period. Cafeterias remained open around the clock, providing free hot meals. The company hired additional medical staff to handle minor injuries immediately on site. A worker who suffered a minor burn or cut could be treated and back on the job within minutes, rather than losing hours going to a hospital. The challenges extended beyond the shipyard itself. Suppliers throughout the steel industry were asked to accelerate their own production schedules. Plate steel needed to arrive on specific days, sometimes specific hours, to maintain the construction schedule. A single late delivery could cascade through the entire process, delaying multiple ships. Dravo's purchasing department operated with military precision, tracking hundreds of suppliers and arranging backup sources for critical materials. Transportation became another critical bottleneck. The Pennsylvania Railroad assigned dedicated locomotives to move prefabricated sections from the fabrication plants to Neville Island. Priority routing gave these shipments precedence over commercial freight. Sections that would normally take 2 or 3 days to transit arrived in hours. When rail transport couldn't meet the schedule, Dravo chartered heavy trucks capable of moving multi-ton steel sections through Pittsburgh's streets. Police escorts cleared routes to prevent delays at intersections. On May 29, 1944, just 58 days after Secretary Forrestal's visit, LST 762 slid down the ways into the Ohio River. It was the 15th ship completed under the Hot Ship program. Dravo had met the impossible deadline with 2 days to spare. The average construction time for these 15 vessels was 3.5 days from keel laying to launch. Not 3.5 months, 3.5 days. The achievement was unprecedented in maritime history. No shipyard anywhere in the world had ever built seagoing vessels of this size and complexity at such speed. The techniques developed during the Hot Ship program became standard practice at all 5 LST shipyards in the Midwest. By the end of 1944, American shipyards were completing an average of 237 LSTs per month. By war's end, over 1,051 LSTs had been built, with 670 coming from the cornfield shipyards of the Midwest. But statistics, however impressive, don't capture the human dimension of this achievement. The LSTs built at Pittsburgh were welded together by men and women from every background American society included. African American welders worked alongside white workers at equal pay. Women operated cranes, welded hull sections, and held supervisory positions. Elderly workers who had been told they were unemployable proved their value daily. Recent immigrants who spoke limited English became skilled craftsmen. The workforce represented American society in all its diversity, united by common purpose and the visceral understanding that their work directly impacted the outcome of the war. At the peak of production in 1944, over 26,000 workers were employed across Dravo's various facilities. The company maintained its own medical clinic, fire department, and police force. 400 workers staffed the cafeterias alone, serving over 40,000 meals per day. The physical plant consumed electricity equivalent to a city of 100,000 people. The welding operation alone used over 70 miles of electrode per week. Supply warehouses stocked over 100,000 different parts and components. The logistics of managing this industrial enterprise rivaled military planning in complexity. Yet for all the impressive production statistics and innovations in welding and prefabrication, the ultimate test would come thousands of miles away on a small volcanic island in the Pacific. The question that mattered was simple and brutal. Did these ships work? Could vessels built by steel workers in Pittsburgh landlocked rivers actually cross oceans, weather storms, approach hostile beaches under fire, and deliver their cargo of tanks and troops where they were needed most? The answer would be written in volcanic sand and blood on the beaches of Iwo Jima, where the concentration of LSTs and the speed of unloading operations would determine the outcome of one of the most savage battles in Marine Corps history. The techniques pioneered at Pittsburgh, the modular construction, the revolutionary welding methods, the assembly line approach that seemed impossible just 3 years earlier, all of it would be tested under the most demanding conditions warfare could impose. And the test would begin with the sound of massive diesel engines roaring to life in the pre-dawn darkness of February 19, 1945. February 19, 1945. H-hour. 6:30 in the morning. The pre-landing bombardment commenced with a violence that seemed to shake the very ocean. 5 battleships on Iwo Jima's eastern coast and 2 on the west opened fire simultaneously. The sound was beyond thunder, beyond anything nature could produce. 16-inch shells weighing over 2,000 pounds each screamed toward the island at velocities approaching the speed of sound. 4 heavy cruisers and 3 light cruisers joined the barrage with 8-inch and 6-inch guns. Destroyers added their 5-inch batteries to the symphony of destruction. Iwo Jima disappeared behind curtains of smoke, flame, and volcanic dust blown skyward by the concussions. Inside the LSTs, waiting 7 miles offshore, the bombardment was felt as much as heard. The ships vibrated with each salvo. Coxswain James Fahey, aboard LST 779, watched Marines in the tank deck checking their equipment one final time. They moved with practiced efficiency, but their faces betrayed the tension. Many were veterans of previous landings. They knew what waited on that beach. At 7:45, the signal came. The first wave of 482 amphibious tractors splashed into the water from their parent ships and began forming up in assigned positions. These LVTs, or landing vehicles tracked, would carry the assault infantry. The Marines would hit the beach first, establishing the beachhead. Then would come the LSTs, with the heavy equipment, the tanks, artillery, ammunition, and fuel that would sustain the attack inland. The volcanic island ahead measured just 4.5 miles long and 2.5 miles wide. Mount Suribachi, a 554-foot volcanic cone, dominated the southern tip. The rest of the island rose in a series of terraces toward the northern plateau. American intelligence had identified 3 Japanese airfields. Capturing these airfields was the mission. B-29 Superfortress bombers flying from the Marianas to attack the Japanese. Homeland needed emergency landing fields. Damaged bombers limping back from raids over Tokyo were being lost in the ocean. Iwo Jima would give them a place to land, refuel, and repair. The strategic value was immense, but intelligence had badly underestimated the defences. Lieutenant General Tadamichi Kuribayashi commanded approximately 21,000 Japanese troops fortified into the most elaborate defensive system ever constructed on a Pacific island. Kuribayashi had abandoned the traditional Japanese strategy of defending at the waterline, where naval gunfire could destroy his forces. Instead, he moved his troops inland and underground. Over 10 months, Japanese engineers had carved out 11 miles of tunnels connecting over 750 major defense installations. Mount Suribachi alone contained 7 stories of tunnels, living quarters, and artillery positions with steel doors protecting the guns. The entire island had been transformed into a fortress designed for one purpose: to kill as many Americans as possible. The first waves of Marines hit the beach at 9:02. For the first minutes, the landing seemed almost unopposed. Marines charged up the volcanic sand terraces expecting withering fire, but encountered only scattered resistance. Officers began to hope the preliminary bombardment had been more effective than expected. Then Kuribayashi's trap sprung. Japanese artillery and mortars, positioned in hardened bunkers throughout the island with interlocking fields of fire, opened up simultaneously. The Marines on the beach were caught in a killing zone. Mortar shells rained down. Artillery fire from positions invisible in the volcanic terrain struck with devastating accuracy. Machine gun fire swept the terraces. Marines tried to dig in, but the volcanic sand was too loose. Foxholes collapsed as fast as they could be dug. The steep terraces prevented vehicles from advancing off the beach. Within minutes, the shoreline became a scene of carnage. At 9:30, the order went out for the LSTs to begin their approach. This was the critical moment. The Marines on shore needed armour support immediately. They needed tanks to suppress Japanese bunkers. They needed artillery to counter enemy guns. They needed ammunition, medical supplies, and reinforcements. All of this sat in the holds of the LSTs wallowing offshore. Lieutenant Robert Landis, commanding LST 779, received the signal and immediately gave orders. Ballast pumps to maximum. Prepare to beach. Deep in the ship's engineering spaces, Pumps roared to life, forcing seawater out of the ballast tanks. The ship rose higher in the water as thousands of gallons of ballast were expelled. The forward draft, which had been 14 feet for the ocean crossing, dropped to under 4 feet. The massive ship, displacing over 4,000 tons fully loaded, now drew less water than many fishing boats. The LST's twin diesel engines, 12-cylinder General Motors behemoths, producing 1,800 horsepower each, pushed the flat-bottomed ship toward shore at 12 knots. The ride was brutal. LSTs were notoriously poor seaboats. The flat bottom and shallow draft meant they rolled excessively even in moderate swells. Sailors joked that LSTs would roll in heavy dew. Now, with the forward draft reduced for beaching, the ship pitched and wallowed like a sick whale. In the tank deck, 14 Sherman tanks sat secured with chains. The tanks weighed 30 tons each, fully loaded with ammunition and fuel. Their crews had been inside for over 2 hours, breathing diesel fumes despite the ventilators. The temperature in the enclosed space exceeded 90 degrees. The noise was overwhelming the rumble of the LST's engines, the clank of chains, the sound of the ship's hull working in the swells. Tank Commander Sergeant Robert McAllister, of the 5th Tank Battalion, Company C, sat in the turret of his Sherman and prayed. Through the open bow doors, McAllister could see Iwo Jima getting larger. Smoke covered the island. Flashes of explosions rippled across the beaches. He could see other LSTs approaching the shore, their distinctive profiles unmistakable. Some were already beached, their bow ramps down, disgorging their cargo. One LST sat burning just off the beach, apparently hit by Japanese artillery. Small landing craft zipped between the larger ships like water bugs. At 9:55, LST 779's flat bottom scraped volcanic sand. The ship shuddered but kept moving, momentum driving it higher onto the beach. The bow rose as the stern settled into deeper water. Lieutenant Landis cut the engines. The ship sat motionless, its bow doors facing directly toward Mount Suribachi, its stern in water deep enough for the protected propellers to function when it was time to retract. Open bow doors, lower ramp. The massive clamshell doors, those quarter-inch steel plates that had been welded together in a Pittsburgh fabrication plant 3 years earlier, swung open with hydraulic precision. The ramp, designed to support 30 tons, hinged down until its forward edge rested on black volcanic sand. From the tank deck, daylight flooded in, along with the smell of smoke, cordite, and something else, the sickly sweet smell of death that already hung over the beach. "Tanks, move out!" The lead Sherman's engine roared. Sergeant McAllister's tank lurched forward, tracks clanking on the steel ramp, then biting into volcanic sand. The weight of the 30-ton vehicle drove the tracks deep into the loose surface. McAllister gunned the engine, tracks churning, fighting for traction. The tank clawed its way up the first terrace. Behind him, 13 more Shermans followed, one after another, spreading out as they emerged from the LST's hold. The entire debarkation took 7 minutes. 14 tanks, each weighing 30 tons, were ashore and moving toward their assembly areas. LST 779 had accomplished exactly what it was, designed to deliver armor directly onto a hostile beach without requiring any shore facilities whatsoever. But the cost was becoming apparent. Japanese artillery observers on Mount Suribachi and the northern heights had perfect observation over the beach. They could see every LST as it approached. The large, slow-moving vessels made tempting targets. As the bow doors opened and the ramps dropped, the LSTs became stationary targets for several minutes, unable to maneuver while discharging their cargo. LST 447, beached 300 yards south of LST 779, took a direct hit from a 150mm howitzer. The shell penetrated the thin hull plating and exploded in the tank deck. Ammunition and fuel ignited. The ship became an instant inferno. Surviving crew members dove over the sides into the surf, swimming desperately away from the burning vessel. Japanese machine guns fired at the swimmers. Some made it to shore, many didn't. LST 779 completed its unloading without taking fire. Lieutenant Landis immediately ordered, "Reverse engines, kedge anchor." The massive anchor, dropped before beaching, now served its purpose. A mechanized winch hauled in the anchor cable, pulling the ship backward. Simultaneously, the twin propellers, protected by their tunnel design, churned at full reverse. The LST's flat bottom, which had allowed it to beach without damage, now let it slide backward off the sand. Within 4 minutes, the ship was in water deep enough to maneuver. It turned and headed back toward the transport area to reload. This was the cycle that would repeat hundreds of times over the next week. LSTs would approach the beach, discharge cargo, retract, return to the transport area, reload, and come back for another run. Each cycle took approximately 2 hours. An individual LST could make 3 to 4 runs per day, delivering tanks, trucks, ammunition, fuel, construction equipment, and personnel. The cumulative effect was staggering. Where previous amphibious operations had been limited by the speed at which cargo could be unloaded from conventional ships using cranes and landing craft, the LST's ability to beach itself and discharge directly onto shore multiplied the rate at which supplies reached the combat zone. By the end of D-Day, February 19th, over 30,000 Marines were ashore on Iwo Jima. They had been delivered by a combination of amphibious tractors, Higgins boats, and LSTs. The casualties were horrific, over 2,400 killed or wounded on the first day alone, the highest single-day casualty rate in Marine Corps history to that point. But the beachhead held, and supplies were flowing. The role of the LSTs became even more critical over the following days. The volcanic sand and steep terraces made the beach one of the most difficult supply operations the Navy had ever attempted. Smaller landing craft often swamped in the surf or got stuck in the sand. LSTs, with their deeper draft and more powerful engines, could maintain position in rougher seas. Their large capacity meant each trip delivered far more cargo than dozens of smaller craft. LST 779 made 4 runs on D-Day, delivering not just the initial 14 tanks but also trucks, ammunition trailers, fuel bladders, and a bulldozer on subsequent trips. Each time the ship approached the beach, Japanese artillery sought it out. Each time, Lieutenant Landis and his crew held their position just long enough to unload, then retracted and escaped. The ship took several near misses. Shrapnel punched small holes in the superstructure. But the hull remained intact, the engines continued running, and the bow doors still opened and closed on command. The durability of LST construction proved itself under fire. These ships, welded together from prefabricated sections in Pittsburgh by workers who had never built seagoing vessels before, absorbed damage that would have sunk more conventional ships. The welded construction, which the Navy had and initially resisted, proved superior to riveting. Where rivets could pop under stress or concussion, welded seams held. The relatively thin hull plating 1/4-inch to 1/2-inch steel was actually an advantage. Artillery shells sometimes punched clean through without exploding, leaving holes that could be repaired with emergency patches. Over the first week of the battle, the tempo of LST operations intensified. As Marines pushed inland from the beaches, they needed continuous resupply. Tank battalions burned through ammunition at prodigious rates, engaging Japanese fortifications that could only be destroyed by direct fire. Artillery battalions fired thousands of shells daily. Medical supplies, water, rations, everything had to come across the beach. The LSTs also began serving roles their designers had never envisioned. Several were converted into temporary hospital ships, loading wounded Marines for transport back to hospital ships offshore. The large tank deck could accommodate dozens of stretchers. Medical personnel established aid stations in the holds, performing emergency surgery and stabilizing casualties for evacuation. The ship's large capacity meant they could evacuate far more wounded per trip than smaller craft. Other LSTs served as floating supply depots. Instead of beaching, they would anchor just offshore and transfer cargo to smaller landing craft. This reduced exposure to artillery fire while still maintaining the steady flow of supplies. The flexibility of LST operations allowed Navy planners to adapt to changing tactical situations. By D+5, February 24th, the beaches had been organized into efficient supply dumps. Steel matting covered the main exits from the beach, giving vehicles solid traction over the volcanic sand. Supply dumps were marked and separated ammunition in one area, fuel in another, rations and water in a third. Shore parties worked around the clock, directing traffic, unloading cargo, and moving supplies forward to the combat units. The Marines were pushing inland, but the cost was staggering. Every yard gained required blasting Japanese positions with demolitions, flamethrowers, and direct tank fire. Casualties mounted. By the end of the first week, over 6,000 Marines were killed or wounded. The original intelligence estimate that the island would fall in 1 week proved disastrously optimistic. The battle would rage for over a month. Throughout this period, the LSTs maintained their supply runs. They operated in all weather, including storms that made the beach approaches extremely dangerous. Several LSTs were lost to weather rather than enemy action, swamped by heavy surf or damaged on the volcanic rocks that lined portions of the shoreline. But the majority continued operating, making run after run, delivering the material that kept the Marines fighting. The human cost aboard the LSTs was significant, but far lower than among the Marines ashore. Naval casualties included crew members killed by artillery fire during beaching operations, men injured in mechanical accidents, and several who drowned when their ships sank. But overall, the LST crews suffered casualty rates far below the 30%, sustained by some Marine units. The ship's crews developed deep respect for the Marines they supported. Many LST sailors watched through binoculars as Marines they had just delivered to the beach were cut down by Japanese fire. The psychological toll was heavy. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By February 23rd, D+4, the 28th Marines had secured Mount Suribachi. A small American flag was raised on the summit, then replaced with a larger flag that could be seen across the island. A Navy photographer captured the second flag raising in what would become the most famous photograph of World War II. The flag itself had come from LST 779. When Marines requested a larger flag, a signalman aboard LST 779 provided the garrison flag from the ship's stores. That flag, measuring 96 inches by 56 inches, became the symbol of American determination and sacrifice. But securing Mount Suribachi was only the beginning. The northern portion of Iwo Jima contained the most elaborate defences. As Marines pushed north, they encountered a nightmarish landscape of pillboxes, bunkers, caves, and tunnels. The terrain was broken and volcanic, providing perfect defensive positions. Japanese defenders fought from positions that were invisible until Marines came within a few yards. Entire squads would be wiped out by fire from positions they couldn't even locate. The Marines adapted. Tank infantry teams developed tactics for reducing Japanese strongpoints. Tanks would provide covering fire while demolition teams worked forward with explosives and flamethrowers. The process was agonizingly slow and costly. A cave complex that looked like it might contain a few defenders could actually shelter 50 or more Japanese soldiers, connected by tunnels to other positions. Clearing each position required close-range fighting with grenades, flamethrowers, and bayonets. Supply remained critical throughout this period. Marine units in forward positions consumed enormous quantities of ammunition. A rifle company might fire more ammunition in a single day on Iwo Jima than it would use in a month of ordinary combat. The LSTs kept the supplies flowing. By the end of February, LSTs had delivered over 100,000 tons of cargo to Iwo Jima's beaches, enough material to fill a freight train over 100 miles long. The battle officially ended on March 26, 1945, 36 days after it began. The cost was staggering. Of the 21,000 Japanese defenders, fewer than 1,000 survived to be taken prisoner. American casualties exceeded 26,000, including nearly 7,000 killed. The Marines had suffered casualty rates approaching 35%. It was the only battle in the Pacific where American casualties exceeded Japanese casualties. But the strategic value of Iwo Jima became apparent almost immediately. On March 4th, while the battle still raged, a damaged B-29 superfortress made an emergency landing on Airfield No. 1. The bomber, returning from a raid over Japan with engine trouble and battle damage, would have crashed into the ocean without Iwo Jima's airfield. The crew of 11 men owed their lives to the Marines fighting and dying a few hundred yards away. Over the following months, Iwo Jima's airfield saved hundreds more bombers and thousands more crewmen. By war's end, over 2,400 B-29 seconds had made emergency landings on Iwo Jima. Each bomber carried a crew of 11. The mathematics were brutal but clear. The capture of Iwo Jima, despite costing 7,000 American lives, saved over 26,000 lives in bomber crews alone. This calculation didn't include the lives saved when fighters based on Iwo Jima began escorting bombing raids over Japan, dramatically reducing bomber losses. None of this would have been possible without the LSTs. The ability to deliver tanks, artillery, and supplies directly onto hostile beaches transformed amphibious warfare. Previous operations required the capture of ports. Iwo Jima had no port facilities whatsoever. Every ton of supplies, every vehicle, every gallon of fuel came across open beaches. The LSTs made it possible. The ships that accomplished this feat had been built in Pittsburgh by workers who had never seen the ocean. They were welded together using techniques developed in emergency conditions just 3 years earlier. They incorporated innovations suggested by a 28-year-old woman welder who had learned her trade in 14 months. They were constructed on assembly lines that reduced ship construction from 12 months to 72 hours. The entire program, from the initial sketch by John Niedermayer to the delivery of over 1,000 completed vessels, took less than 4 years. This represented industrial mobilization on a scale unprecedented in human history. The American economy produced not just LSTs but thousands of other vessels, tens of thousands of aircraft, millions of vehicles, and unfathomable quantities of ammunition, fuel, food, and equipment. The United States outproduced the combined industrial capacity of Germany, Japan, and Italy by factors of 3 to 1 or greater in most categories. But raw production numbers, however impressive, don't fully capture what made American industrial mobilization effective. The LST program succeeded not just because America could build ships quickly, but because American industry could adapt, innovate, and solve problems in real time. When traditional shipbuilding proved too slow, new methods were invented. Skilled labor was scarce. Training programs created new workers. When existing materials were insufficient, alternatives were found. This flexibility and adaptability, as much as raw productive capacity, determined the war's outcome. The workers who built the LSTs represented American society in all its diversity. Women comprised a significant portion of the workforce, performing skilled labor in welding, machining, and crane operation. African Americans worked alongside white workers at equal pay, a revolutionary practice for the 1940s South, even though Pittsburgh was northern. Elderly workers, people with disabilities, recent immigrants all found places in the shipyards. This inclusive workforce wasn't the result of idealistic social policy. It was practical necessity. America needed every capable worker to win the war. The legacy of the LST program extended far beyond World War II. The construction techniques developed at Dravo and other shipyards, prefabrication, modular construction, welding instead of riveting, became standard practice in the shipbuilding industry. After the war, these methods spread internationally. Japanese shipbuilders, studying American techniques, adopted and refined them to build the most efficient shipyards in the world by the 1970s. The social changes unleashed by wartime production proved equally lasting. Women who discovered they could weld, operate heavy machinery, and supervise workers didn't forget these capabilities when the war ended. Many left industrial work after 1945, but they had proven what women could accomplish given opportunity and training. This experience fed into the women's rights movements of subsequent decades. Similarly, African American workers who had experienced equal pay and skilled positions during the war were less willing to accept discrimination afterward. The civil rights movement of the 1950s and 60s had roots in wartime experiences that demonstrated racial discrimination had no factual basis. For the individuals involved, the LST program remained a source of pride for the rest of their lives. Margaret Wilson, whose welding sequence innovation helped reduce LST construction time, worked at Dravo until retirement in 1976. In interviews late in life, she recalled the war years with mixed emotions: pride in contributing to victory, sorrow for the casualties, and amazement at what had been accomplished. "We didn't think about whether it was impossible," she said. "We just did what needed to be done." Lieutenant Robert Landis, who commanded LST 779 through the Iwo Jima operation, made 12 runs to the beach during the battle. His ship delivered over 200 vehicles, 3,000 tons of supplies, and evacuated over 800 wounded Marines. LST 779 survived the war, served in the Korean conflict, and was finally decommissioned in 1955. Landis remained in the Navy, retiring as a port captain in 1963. He credited his survival and success to the ship beneath his feet, the sturdy, ugly, indispensable LST that had been welded together in Pittsburgh by people he never met. Sergeant Robert McAllister, whose Sherman tank was the first off LST 779 at Iwo Jima, survived the battle but was wounded on March 8 when a Japanese mortar round exploded near his tank. He recovered from his wounds and returned home to Pennsylvania. He worked as a steel worker in Pittsburgh for 35 years after the war. In the 1980s, he visited the Dravo shipyard and met some of the workers who had built LSTs. The meeting was emotional. The workers had known their ships went to war but had never met the men who fought from them. McAllister thanked them for building a ship that could deliver him and his tank safely to the beach. One elderly welder, a woman named Dorothy Simmons, told him she had welded sections of over 50 LSTs. She wanted to know if her work had been good enough. McAllister assured her it had saved his life. The LST program's success at Iwo Jima validated every innovation and shortcut taken during construction. The ships performed exactly as designed under the worst possible conditions. They absorbed damage and continued operating. They delivered cargo in weather that grounded smaller craft. They adapted to roles their designers hadn't envisioned. Most importantly, they gave American commanders the capability to land overwhelming force anywhere there was a beach, transforming amphibious warfare from a specialized, risky operation into America's primary method for projecting power against island and coastal objectives. The strategic implications were profound. Japan's defensive strategy relied on making every invasion so costly that Americans would negotiate a peace rather than attack the home islands. But LSTs, combined with the ability to produce them in unlimited quantities, meant America could absorb casualties and continue attacking. No defensive line could hold against an enemy that could land armies anywhere along a 1,000-mile coastline. Japan's defensive calculations, based on limiting American landing capabilities, became obsolete. After Iwo Jima, LSTs participated in the even larger invasion of Okinawa, where over 343 LSTs supported Marine and Army divisions. The ships proved equally vital in that 3-month battle. Plans for the invasion of the Japanese home islands, scheduled for November 1945, called for over 600 LSTs in the initial assault waves alone. The atomic bombs that ended the war in August 1945 meant those plans were never executed, but LST construction continued until the Japanese surrender. The war's end found over 1,000 LSTs in service around the world. The Navy faced the question of what to do with this enormous fleet. Many were simply scrapped. Others went into reserve storage, mothballed against future need. Some found commercial uses. LST 393, for example, was converted into an automobile ferry on Lake Michigan, carrying cars between Muskegon and Milwaukee for decades before being restored as a museum ship. Several hundred LSTs returned to service during the Korean War, participating in the Incheon landing in 1950. The same ships that had landed on Iwo Jima now landed troops and tanks in Korea. Their capabilities remained relevant. By the 1950s, many military theorists had argued that atomic weapons made amphibious operations obsolete. The success at Incheon proved otherwise. Amphibious capability, and the LSTs that enabled it, remained vital to American military power. The LST design itself evolved. In the 1950s and 60s, the Navy built Newport-class LSTs with improved speed and capability, though they abandoned the traditional bow doors in favor of a deployable ramp system. Modern amphibious warfare ships trace their lineage directly to the World War II LST. The basic concept, a ship that can cross oceans, approach hostile shores, and discharge cargo directly onto beaches, remains central to naval amphibious operations. Today, original World War II LSTs are rare. Most were scrapped decades ago. A handful survive as museum ships, carefully preserved as artifacts of the war. LST 325, fully restored to operational condition, tours American ports, allowing the public to walk the decks and experience what it was like aboard these vessels. The ship draws crowds wherever it docks. Veterans who served aboard LSTs come to reunions, many bringing children and grandchildren to show them where Grandpa spent the war. These museum ships provide tangible connection to history. Visitors can stand in the tank deck and imagine it filled with Sherman tanks and Marines waiting to go into combat. They can see the bow doors and understand how revolutionary it was to simply drive tanks off a ship directly onto a beach. They can appreciate the cramped crew quarters, the simple but effective engine room, the bare-bones simplicity that made rapid production possible. But more than physical artifacts, the LST program represents a particular moment in American history when crisis produced innovation and society mobilized toward common purpose with extraordinary effectiveness. The challenge seemed impossible: build ocean-going ships in landlocked cities, train workers with no experience, develop entirely new construction techniques, and do it all faster than anyone thought possible. Yet it was accomplished, and accomplished at a scale that determined the outcome of the largest war in human history. The lessons resonate beyond military history. When confronted with problems that seem insoluble, human creativity and determination can find solutions. When traditional methods prove inadequate, new methods can be invented. When skilled labor is unavailable, people can be trained. When time is critical, processes can be accelerated without sacrificing quality. These lessons apply as much to peacetime challenges as to wartime crisis. The LST program also demonstrates that diversity isn't just morally right, but practically advantageous. The inclusive workforce at Dravo performed better than would have been possible if the company had limited itself to traditional hiring practices. The woman who improved welding sequences, the African-American workers who trained white workers in specialized techniques, the elderly craftsmen who shared decades of experience, the recent immigrants who brought skills from their homelands all contributed essential capabilities. Excluding any group would have reduced overall effectiveness. Finally, the LST story illustrates the crucial role of logistics in modern warfare. Battles are fought by soldiers with rifles and tanks, but wars are won by the industrial capacity to produce rifles and tanks, the ships to transport them, the supply chains to keep them fueled and ammunition loaded, and the medical capability to treat casualties and return them to duty. The Sherman tanks that fought on Iwo Jima were important, but equally important were the LSTs that delivered them there, the welders in Pittsburgh who built the LSTs, the steel mills that produced the plates, the railroads that transported materials, and the entire industrial ecosystem that made American military power possible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.